Okay, let's unpack this. Imagine putting an electric vehicle through its absolute paces.
Right.
You're pushing a hybrid dual motor system on a track, doing maybe 70 or 80 miles an hour.
Yeah, moving fast.
Very fast. And you hit a corner and just stomp on the brake.
Hmm.
At that precise millisecond, you expect maximum regenerative braking. You expect the system to just seamlessly siphon all that kinetic energy right back into the battery pack.
Exactly. That's the ideal scenario.
Right. But instead, a cascading failure in the power electronics triggers this unmitigated, 1200-volt spike directly into the inverter.
Oh, yeah.
We aren't talking about a simple check engine light here. We are talking about forces powerful enough to vaporize silicon carbide chips, shatter capacitors, and just unleash lethal high-voltage energy right there on the chassis.
Yeah, it's the kind of catastrophic failure that keeps powertrain engineers awake at night, honestly.
I can imagine.
In the realm of functional safety, what you just described, an uncontrolled DC link overvoltage event that is universally categorized as an ASIL B level threat.
ASIL B.
Yeah, Automotive Safety Integrity Level B. It demands this incredibly sophisticated, multi-layered mitigation strategy because, well, the sheer amount of kinetic energy being converted into electrical energy at highway speeds is just staggering.
It's massive. And that's exactly why we are opening up a particularly dense source document today for this deep dive. We are looking at the Functional Safety and Fault Diagnostics Master List for Hybrid Dual Motor PCS Systems.
This is quite the title.
It is. It is the definitive engineering playbook, but we are bypassing the general overviews and dropping straight into the trenches of Section B04.
Oh, Section B04?
Yeah, which deals exclusively with this DC link overvoltage issue. We're going to look at the physics of how this failure manifests, the hardware that catches it in fractions of a millisecond, the design architecture that mathematically prevents it, the obsessive factory floor controls, and finally, the physical torture tests these systems endure before they ever see a public road.
Sounds like a plan.
Yeah.
The best place to start is really with the physical reality of what happens when a spinning motor becomes a liability rather than an asset.
Right.
The document highlights regeneration and field weakening failure as the primary root cause.
Okay, field weakening failure.
Yeah. So when that dual motor setup is spinning at something crazy, like 12,000 revolutions per minute,
Wow.
the motor's natural back electromotive force, the back EMF,
Right.
is actually much higher than the voltage of the battery pack itself.
Right, because any permanent magnet motor kind of acts as a generator when it spins, right?
Exactly.
The faster the rotor spins, the higher the voltage it generates.
You got it.
If the back EMF exceeds the DC link voltage, current would normally flow uncontrollably back into the battery. So to push the motor to 12,000 RPM in the first place, the inverter has to constantly inject a specific opposing magnetic field.
The axis current, yeah.
Right, to artificially weaken the rotor's magnetic flux.
Right. And that field weakening control loop is highly dependent on knowing the absolute exact mechanical angle of the spinning rotor,
Okay.
usually via a sensor called a resolver.
Gotcha.
But what happens if you introduce a severe mechanical vibration?
Like hitting a huge pothole.
Yeah, or a sudden thermal shock that skews the resolver's analog feedback. The microcontroller loses the rotor angle.
Oh.
The control loop just collapses. The inverter instantly stops injecting that opposing D-axis current.
So the artificial suppression just vanishes.
Oh.
Wow.
The full, unsuppressed magnetic flux of the rotor slams back into the stator windings.
Ouch.
The back EMF spikes exponentially. Because the internal freewheeling diodes of the inverter are forward biased by this massive voltage, the motor basically forces its way into uncontrolled generation.
It just dumps a tidal wave of uncontrolled power directly onto the DC link bus.
Yeah, it's brutal.
It's the equivalent of riding a fixed-gear bicycle down a really steep mountain pass.
Oh, that's a good way to look at it.
Right. As long as your legs are keeping up with the pedals, you are controlling the descent.
Right.
But if your feet slip,
You're in trouble.
yeah, the mechanical linkage doesn't break. The wheels forcefully drive the pedals out of control.
Exactly.
The kinetic energy of the mountain just violently transfers into the bike's mechanics until something shatters. In the EV, the fixed mechanical connection to the road is driving a generator that is blasting the DC link with a voltage it just wasn't rated to handle.
Yeah, and that physical coupling to the road makes it a sustained threat, too.
It doesn't just stop.
No, it's not a momentary blip. As long as the car is rolling, that generator is pumping out lethal voltage.
Man.
But Let's look at a scenario where the system actually is operating correctly during a heavy braking event.
Okay.
But the threat comes from the other side of the circuit,
What's that?
the load dump.
Oh, right. This is where the battery management system, the BMS, steps in and essentially pulls the plug, right?
Exactly. The BMS has one overriding prime directive.
Protect the battery.
Protect the lithium-ion cells at all costs.
Right.
If you are braking aggressively from high speed, you are pushing hundreds of amps of regeneration current back into the battery.
That's a lot of juice.
It is. If the BMS calculates that the cell temperatures are spiking, or that the charge rate might induce lithium plating on the anodes,
Which is bad.
very bad, it will protect the pack by immediately opening the high-voltage contactors. It physically severs the connection to the battery in less than 100 microseconds.
Okay, let's track the physics here, because we have a massive wave of kinetic energy being translated into electrical current by the motors, flowing back through the inverter, heading straight for the battery,
Yeah.
and a mechanical relay just slams shut. The energy is already in the pipes.
Yeah.
Where does it go?
What's fascinating here is the only place it can go is the DC link capacitor.
Oh, boy.
Now, the capacitor bank is there to smooth out voltage ripple and provide instantaneous current for switching.
Right.
It is absolutely not sized to absorb the total kinetic energy of a 2-ton vehicle.
Right. I mean, that's not its job.
Exactly. The moment the contactors open, you're forcing that massive regeneration current into a relatively small capacitance. According to the formula, change in voltage over time equals current over capacitance.
The voltage on that DC bus will skyrocket.
A nominal 400-volt system will spike to 900, 1,000, or even 1,200 volts in fractions of a millisecond.
It is forcing a fire hose into a water balloon.
That's perfectly put. The voltage exceeds the avalanche breakdown rating of the silicon carbide chips in the inverter, and they physically rupture.
Just pop.
They punch right through. You lose the semiconductor junction, which usually results in a dead short across the bus, which then vaporizes the internal wire bonds.
Good grief.
But even if the BMS behaves perfectly, and the resolver tracks the rotor perfectly, there's a third failure mode that relies purely on the physical geometry of the hardware.
This is the V-spike. Right.
Yeah, the V-spike induced by parasitic inductance.
This gets into the reality of switching high power very fast. Because modern inverters use silicon carbide, or SOOT chips, right? Because they can switch on and off in mere nanoseconds.
Right.
That incredible change in current over time is great for efficiency, but it turns the physical wiring into a liability.
It invokes Faraday's law of induction.
Okay.
To move hundreds of amps between the capacitor and the power modules, the inverter uses heavy copper bus bars.
Thick chunks of metal.
Yeah, but every physical conductor has stray, parasitic inductance. It's an inescapable property of the geometry.
Okay.
Inductance essentially gives the electrical current momentum.
Wait, so just the physical shape or layout of a thick metal bar can magically create extra destructive voltage?
Yes.
So it's exactly like a water hammer in playing.
Oh, exactly.
You have water flowing rapidly through an iron pipe. If you suddenly slam a mechanical valve shut, the physical momentum of that heavy water crashes against the valve, creating a pressure spike that can rupture the pipe.
That is the exact mechanism. In the inverter, the magnetic field surrounding the copper bus bar stores energy. When the 6E chip snaps shut to turn off the current in a few nanoseconds, that magnetic field collapses aggressively.
Resisting the change?
Right, resisting the change in current flow. This rapid collapse induces a massive localized voltage spike across the terminals of the chip.
Wow.
So even if the main DC link voltage is sitting safely at 400 volts, the parasitic inductance can overlay a transient spike that pushes the local voltage at the silicon beyond its destruction point.
Which means the physical shape of a seemingly inert piece of copper acts as a voltage multiplier if you switch the current fast enough.
Yeah, it forces engineers into a really tight corner.
I bet. But the document outlines a fourth cause that doesn't actually destroy the hardware.
Oh, right.
It just destroys the microcontroller's perception of reality.
Yes.
Ghost signals from ground loops.
This one is tricky. When we talk about these chips switching at nanosecond speeds, we aren't just dealing with massive current changes. We are also generating extreme voltage changing at rates exceeding 10 kilovolts per microsecond.
That's so fast.
That rapid voltage fluctuation creates immense electromagnetic interference. It capacitively couples through the heat sinks and chassis, creating common mode noise.
Okay, so if the grounding layout isn't pristine, that high-frequency noise finds a way to bleed back into the low-voltage analog measurement circuits.
Exactly. The microcontroller's sitting there trying to read a delicate analog signal from the DC link voltage sensor. But this common mode noise gets superimposed onto the signal lines.
It gets garbled.
Right. The analog-to-digital converter samples this noisy line and calculates that the DC link voltage just spiked to 1,000 volt.
Even though it didn't.
The voltage is actually completely normal.
Wow.
But the controller thinks the system is having a catastrophic overvoltage event.
All right.
And it triggers an emergency shutdown while the car is doing 70 miles an hour on the highway.
It hallucinates an emergency.
Basically, yeah.
So we have uncontrolled generation from a lost rotor angle, a load dump from a panicking battery, microscopic water hammers from copper bus bars, and a microcontroller hallucinating ghost voltages.
It's quite the list.
It really is. To combat all of this, the architecture has to detect and suppress these threats faster than the physical limits of the materials. So we are moving out of the root causes and into the technical architecture.
Right. The front line of this defense matrix is isolated voltage sensing.
Okay.
Because of that severe common mode noise we just discussed, you can't simply run a resistor divider network from the 800-volt DC link straight into the microcontroller.
Right, the noise would just corrupt the reading instantly.
Instead, the architecture utilizes highly isolated delta sigma modulation.
Okay, so rather than sending a variable analog voltage across the board, the delta sigma modulator sits right next to the high voltage bus, right? It samples the voltage millions of times a second and immediately converts it into a high-frequency 1-bit digital bit stream.
Exactly. And that digital bit stream is passed across a robust galvanic isolation barrier.
Like an optical isolator.
Yeah, optical or capacitive. The microcontroller on the other side receives just ones and zeros, completely immune to the analog noise of the inverter.
That's brilliant.
It uses an internal sync filter to decimate that bit stream back into a high-precision voltage reading.
Wow.
By digitizing and isolating the signal right at the source, you guarantee that the brain of the car has an absolute uncorrupted view of the DC link.
That solves the hallucination problem.
It does.
But here's where it gets really interesting. What if the main microcontroller, the brain that is supposed to interpret that signal and take action, is currently, I don't know, executing a complex task? Or worse, what if it hangs up and freezes right as a voltage spike occurs?
Oh, that's the nightmare scenario.
A software context switch takes time, and we are operating in a window of microseconds here.
You're absolutely right. This is a critical point in functional safety. You cannot rely solely on software to prevent a hardware explosion. That introduces the concept of hardware bypassing.
Okay.
The source document specifically mandates the use of an isolated smart gate driver, like the MC33GD31X6 series.
That's a mouthful.
It is, but it's a lifesaver.
Yeah.
This chip sits directly between the microcontroller and the physical switches. It has its own dedicated analog desaturation and overvoltage monitoring circuits hardwired in.
So it's an analog watchdog that doesn't need to boot up, run code, or wait for an interrupt routine.
Exactly. It requires no software overhead.
Wow.
If this smart driver detects the DC link voltage skyrocketing and it sees that the microcontroller isn't responding fast enough,
It just takes over.
it autonomously overrides the system. In under 100 microseconds, it executes an active short circuit, or ASC.
Okay, let's pause on the active short circuit. Because to a layperson, intentionally short-circuiting a high-voltage system sounds like the exact opposite of safety.
I know, it is entirely counterintuitive.
Right?
But remember the physics of the uncontrolled generation. The motor is pumping voltage into the DC link.
Yep.
To stop it, the smart gate driver turns on all three of the upper switches in the inverter, or all three of the lower switches simultaneously.
Okay.
This physically shorts the three motor phases together.
Wow. So by shorting the phases together at the inverter, the back EMF never reaches the DC link. The voltage on the bus is clamped to whatever the capacitor currently holds.
Exactly.
But wait, the energy from the spinning motor still exists. Where does it go?
Well, it gets burned off as heat right there inside the motor stator windings.
Oh, I see.
You are trading a catastrophic explosive voltage spike at the inverter for a rapid, intense thermal spike inside the massive copper mass of the motor.
And the motor can handle that.
Yeah, the motor can thermally absorb that punishment far better than the fragile silicon chips can handle an overvoltage.
That makes sense. That tackles the motor pushing power in.
Right.
But let's go back to the low dump scenario.
Yep.
The battery contactors have opened, the inverter clamped the motor. But you still have whatever energy was trapped in the massive DC link capacitors at the exact moment the fault occurred.
Yeah.
If the car has just been in a physical collision, you have an incapacitated vehicle sitting there with 800 volts of lethal energy just waiting across the bus bars.
And that is an immediate lethal threat to first responders or tow truck drivers.
Yes.
So the architecture includes an active discharge circuit.
A 2-second rescue.
Exactly.
Okay.
When a crash is detected or an ASIL B level fault shuts down the system, a dedicated solid-state switch aggressively dumps all the stored energy from the DC link capacitors into a massive, heavy-duty discharge resistor.
And the specification requires pulling an 800-volt bus down to a touch-safe level, typically under 60 volts, in less than 2 seconds, right?
Yes. It is a violent dissipation of energy. We're talking about converting hundreds of joules of electrical energy into pure heat almost instantly.
That sounds intense.
The thermal mass of that discharge resistor has to be carefully calculated so it doesn't melt its own solder joints during the process.
Yeah, I'd imagine.
But the priority is absolutely clearing the high-voltage shock hazard.
Right, so the human stakes are covered.
Absolutely.
So the hardware architecture is built around absolute autonomy. You've got isolated sensing, autonomous analog clamping, and hardwired energy dumping.
Yep.
But the software isn't just sitting idle. The source text outlines a 2-tier software fallback strategy for managing transients before they reach that hard-coded explosion point.
Right. The microcontroller operates in a predictive capacity.
Okay.
If the DC link voltage hits an initial warning threshold, say 720 volts on an 800-volt architecture, the software transitions into a derated limp mode.
Like a safe mode.
Basically, it might actively alter the DAG axis and coaxis current commands to reduce torque or change the switching frequency to suppress regenerative spikes.
It tries to dynamically walk the system back from the edge.
Exactly. But if the voltage continues to climb and hits the critical threshold, the software has a strict fault-tolerant time interval, the FTTI, of 60 milliseconds to take definitive action.
And the text points out a really nuanced challenge here regarding high-speed faults.
Oh, yeah. If the car's moving slowly, the software can just command all the switches to open, allowing the motor to naturally freewheel.
Sure.
But if the motor's at 12,000 RPM, opening the switches guarantees that massive back EMF wave we talked about.
Right, the tidal wave.
So the software must trigger an active short circuit. But instantly slamming all 3 phases into a short circuit at top speed creates a massive, violent, transient torque ripple.
The magnetic field violently opposes the rotation so fast that the mechanical shear forces could snap the rotor shaft or shred the reduction gears.
You protect the inverter, but you drop the transmission on the highway.
Which is obviously bad.
Very bad. So the software executes a stepwise active short circuit.
How does that work?
Instead of shorting all 3 phases instantly, it shorts just 2 of the phases together for a carefully calculated duration, usually around 1 to 2 milliseconds.
Okay.
This 2-phase short creates a localized magnetic cushion.
Oh.
It allows the zero-sequence currents to build up more gradually, absorbing the massive initial kinetic shock.
Smart.
Once the mechanical transient settles, the software throws the 3rd phase in, establishing the full, stable 3-phase short circuit.
It's an incredible sequence. The software deliberately cripples the motor in a staggered asymmetrical rhythm to prevent snapping its own mechanical bones, all while keeping the electrical spike under the 720-volt ceiling.
Yeah.
And it orchestrates this entire sequence in under 60 milliseconds.
It highlights how electrical and mechanical engineering are inextricably linked in these systems.
They have to be.
And that leads perfectly into the next phase of the document.
Right.
We've covered how the system reacts to a crisis. But how do you design the physical blueprints to ensure these crises are statistically improbable in the first place?
This is the DFMEA phase, design failure mode and effects analysis, transitioning from reactive defense to proactive design.
Exactly. Let's start with that parasitic inductance problem.
Yes, let's. We established that the stray inductance in the copper bus bars creates that localized voltage V spike when the SISTI chips turn off. You can't turn off Faraday's law.
Nope.
So how did the engineers mitigate the physics of the V spike during the actual design phase?
Through aggressive geometric optimization. The design rule mandates a strictly low inductance layout.
Okay, what does that look like?
Instead of routing the positive and negative high-voltage bus bars alongside each other, engineers use laminated bus bars.
Oh, like a sandwich.
Literally.
Yeah.
They take a wide, flat sheet of copper for the positive rail and a wide, flat sheet for the negative rail, and they physically sandwich them tightly together.
Wow.
They're separated by an incredibly thin layer of high dielectric insulation like Captain Polyamide.
So by routing the positive current directly on top of the returning negative current, their magnetic fields are perfectly opposed.
Exactly. They rely on mutual inductance to cancel out the self-inductance.
That is so clever.
The proximity effect and the skin effect are manipulated to basically crush the overall loop inductance. By forcing those conductors mere millimeters apart, they can drop the stray inductance from over 100 nanohenries in a sloppy design down to less than 15 nanohenries.
Wow. And that physical proximity drastically limits the energy stored in the magnetic field.
Yep.
Which in turn mathematically caps the amplitude of the V-spike when the chip switches.
That's exactly right.
But getting heavy copper that close together introduces severe tolerance issues, right? Which brings us to the bomb law.
Automotive designers outright ban the use of standard, off-the-shelf commercial electronics.
Makes sense.
Consider the voltage sensing circuit we discussed, the delta sigma modulator. It relies on a resistor divider and filter capacitors to scale down the 800-volt signal. If you use a standard X7R ceramic capacitor for that filter, its capacitance fluctuates wildly depending on the ambient temperature.
Oh, wow.
It also suffers from dielectric absorption, meaning it effectively remembers previous voltages, skewing real-time measurements.
That sounds like a nightmare for precision.
It is. And standard high ceramics exhibit the piezoelectric effect.
Oh, where mechanical stress creates voltage.
Yes. If the car drives over a pothole, the physical mechanical vibration of the chassis causes the ceramic material to physically compress, generating its own microvoltage spike.
So the vibration of the road becomes electrical noise injected directly into your safety monitor.
Yes, the car could literally hallucinate an overvoltage just because you hit a bump.
Unbelievable.
That is why the DFMEA strictly mandates the use of Class 1 COG, or NP0 dielectric ceramics.
COG capacitors use a specific calcium zirconate formulation, right? They are incredibly stable.
They are essentially immune to the piezoelectric effect, and their temperature coefficient is 0, hence C0G. Whether the inverter is parked in a sub-zero blizzard at negative 55 degrees Celsius or baking under maximum load at 125 degrees Celsius, the capacitance does not shift.
Total stability.
Exactly. When you pair those with ultra-precise thin-film resistors boasting 0.1% tolerances and extremely low temperature coefficients, you construct a sensory circuit that is environmentally immortal.
Environmentally immortal, I love that. The calibration just never drifts.
Ever.
And the design philosophy extends all the way into the metallurgy of the motor itself. The DFMEA dictates that the physical geometry of the motor, the strength of the permanent magnets and the winding density of the stator, must provide an intrinsic fail-safe sealing.
Yes, it relates to the motor's back EMF constant, the key value. Designers deliberately tune the magnetic flux linkages so that even if the software completely fails and the motor goes into maximum uncontrolled overspeed.
Like the absolute worst-case scenario.
Right. The absolute peak open circuit voltage it can physically generate remains below 80% of the silicon carbide chip's breakdown voltage.
So they artificially constrain the raw power of the motor. Even at terminal velocity, the physical magnets simply aren't strong enough to melt the inverter.
Exactly.
It's a fundamental physics firewall.
It requires trading away some high-end torque and efficiency, sure, but when the alternative is an ASIL B catastrophic failure, it's a mandatory design compromise.
Right. But of course, a gray blueprint is useless if the factory worker makes a mistake.
Oh, absolutely.
Yeah.
The most flawless mathematical model in CAD means nothing if it is assembled incorrectly.
Right. Which brings us out of design and onto the factory floor. The PFMEA phase, process failure mode and effects analysis.
Right.
This section of the document is fascinating because it focuses entirely on eliminating microscopic variables during mass production.
Yeah, it goes deep.
For example, banning the human hand. Manual tightening of high-voltage connections is universally banned. You cannot have a factory technician using a standard click-type torque wrench on a DC-link busbar.
Nope. Because a standard torque wrench only measures the twisting force required to turn the fastener.
Right.
But on a high-voltage, high-current connection, we don't care about twisting force. We care about clamping force.
Okay, I see.
If the busbar connection is even slightly loose, it introduces microohms of contact resistance. When you push 400 amps through a loose connection, I²R losses dictate that it will generate intense localized heat.
And then the copper oxidizes, the resistance increases further, the heat spirals, and you end up with thermal runaway and a vehicle fire.
Exactly. So the factories enforce the use of torque angle servo screwdrivers.
Okay, how are those different?
The servo screwdriver measures the rotational torque, but it simultaneously tracks the exact rotational angle of the fastener in degrees.
Oh, wow.
It cross-references a perfect force displacement curve in real time. It knows exactly how far the bolt has traveled down the thread pitch.
So if there is a burr on the thread, a standard wrench would click early, leaving a loose joint.
Right, but the servo driver sees that the torque spikes without the corresponding angular rotation, flags a fault, and halts the line.
That is incredibly smart. But the text notes that for this torque angle calculation to work, the friction of the bolt has to be a known mathematical constant, which introduces the use of optical character recognition and visual scanning just for the bolts.
Yeah, it sounds like overkill, but it's necessary. The robotic feed system visually inspects every single fastener before it's driven.
Just to check the coating.
Yep. It verifies that the bolts are coated with a highly specific zinc flake or phosphate coating.
Okay.
This coating isn't just for corrosion resistance. It guarantees a highly precise coefficient of friction or value. If the vision system detects a non-conforming coating, it rejects the bolt. They control the metallurgy of the bolt coating to ensure the servo algorithm remains perfectly calibrated.
That obsession with calibration continues into the end-of-line, or EOL, testing, too.
Oh, definitely.
Because even with C or G capacitors and thin film resistors, mass manufacturing always introduces microscopic gain and offset errors in the analog front end of the inverter.
You cannot rely on theoretical component values, ever.
Right.
Every single inverter is connected to an automated test rig at the end of the line. The rig injects a highly precise, externally calibrated reference voltage into the DC link.
Okay.
It records what the inverter's internal sensors read at room temperature. Then, they heat the unit to 85 degrees Celsius and run the sweep again.
Oh, I see. So they map out the exact bespoke analog deviations of that specific piece of silicon.
Exactly. And then the factory computer calculates a unique algorithmic correction factor and digitally burns it into the inverter's EEPROM memory. Every inverter that leaves the factory is uniquely digitally tailored to offset its own physical imperfections.
That level of detail is staggering. But the final PFMEA control is the one that really underscores the stakes. The helium sniffer. The motor and the inverter must be heavily liquid-cooled to shed the massive heat generated by the secret switching losses. Right?
That's right.
But routing liquid coolant adjacent to an 800-volt DC link is inherently dangerous. If a single drop of ethylene glycol breaches the cooling jacket and touches the bus bars, it creates a dead short.
You would be an instant uncontained arc flash. So the cooling channel seals have to be perfect.
Wait, they use high-precision helium leak testing like we are building a spacecraft just to check a motor casing.
If we connect this to the bigger picture, a tiny coolant leak into the 800 V bus bar will cause a catastrophic short.
Right.
But standard pressure decay testing, where you pump the chamber full of compressed air and watch a pressure gauge, is not sensitive enough.
Because the molecules are too big.
Exactly. The molecular structure of air or water is relatively large. A labyrinth path microcrack in an aluminum casting might hold air pressure for a 10-minute factory test, but over 5 years of harsh thermal cycling and road vibration, it will eventually allow coolant to weep through.
So they turn to mass spectrometry and helium gas. Helium atoms are incredibly small. They will readily slip through microscopic porosities that larger molecules can't penetrate.
Yes. The factory seals the coolant jacket, pulls a hard vacuum, and backfills the passages with helium.
Wow.
A hypersensitive mass spectrometer probe, the helium sniffer, scans the exterior of the casing.
That's wild.
And the pass-fail criteria is merciless. The leak rate must be below 10 to the -5th millibar liters per second.
Goodness.
It is aerospace-grade hermetic verification to ensure the liquid and the high voltage never meet.
Okay, which brings us to the final hurdle. How do they prove this all works before they sell it to the public? The engineers designed a mathematically sound system. The factory built it with robotic perfection and helium-tested seals. Now, Section 5, the DVPNR, the Design Verification Plan and Report.
The torture test.
Right. Before this architecture goes into production, they have to physically torture it in the lab to prove that the millisecond defense matrix actually works.
And the cornerstone of this validation is the physical dyno load dump test.
How does that work?
They don't just simulate this. They bolt the physical hardware to a massive dynamometer. They spin the motor up to its absolute maximum speed, say 12,000 RPM, under full torque load.
Okay.
They command the inverter to execute maximum regenerative braking, pushing peak current back toward the battery emulator.
Sure, screaming.
And right at the peak of that power surge, when the DC link is flooded with energy, they intentionally rip the high voltage contactor open.
They just yank it.
They induce the absolute worst-case scenario load dump. The hardware must survive entirely on its own merits. The MC33GD31X smart driver chip has to detect the rapidly rising voltage on the bus. It must override the microcontroller and trigger the active short circuit in less than 100 microseconds.
That is so fast. They must be looking at high-speed oscilloscopes to verify that the voltage spike never breaches the 720-volt or 800-volt maximums.
Oh, constantly. And they have to ensure that the short circuit phase currents don't exceed the safe operational limits of the silicon, say, 550 amps.
Right.
If the DC link capacitor bulges, or if a single SiC MOSFET suffers avalanche breakdown, the entire platform fails the test.
They induce a catastrophic hardware stroke just to prove the automated defibrillator works perfectly.
That's a great way to put it. And they apply that same brutality to the active discharge system with the 100-strike lightning test.
Right. We talked about how the discharge resistor has to convert 800 volts of energy into heat in under 2 seconds.
Right. And in the lab, they place the entire inverter into an environmental chamber heated to 85 degrees Celsius.
Why so hot?
They are simulating the worst-case ambient temperature of an engine bay on a hot summer day.
Ah.
The system is already thermally stressed. Then they force the active discharge switch to dump the full bus voltage into the resistor.
And they don't give it time to cool down.
No, they immediately recharge the bus and trigger it again and again. 100 consecutive strikes.
100 times.
The validation requires that the heavy-duty resistor absorbs that immense thermal cycling without the resistance drifting out of spec, without melting the solder joints on the PCB, and most critically, without igniting.
Right. The fail-safe system cannot become the source of a vehicle fire itself.
Exactly.
It's an incredible test of material science. But physical hardware tests can only go so far when evaluating complex software behaviors, right?
Yeah, you hit a wall eventually.
That's why the document highlights hardware in the loop, or HIL, sabotage for validating the software fallback strategies.
HIL testing is amazing. Yeah. It bridges the physical and the virtual.
Also.
They take the actual physical microcontroller board that runs the car, the real silicon, and they wire its sensory inputs and control outputs directly into a high-fidelity supercomputer.
Okay.
The supercomputer runs a massive, real-time physics engine that simulates the motor's magnetic fields, the mechanical inertia of the drivetrain, and the electrical dynamics of the battery.
So, to the physical microcontroller, it believes it is driving a real car down a real highway.
Exactly.
Wow.
And while the simulated car is doing 12,000 RPM, the engineers intentionally introduce virtual sabotage.
Like what?
They might inject a severe gain error into the resolver feedback loop, or simulate a severed wire on a voltage sensor. They instantly blind the microcontroller.
Just to see what it does.
Right. This tests the software's ability to detect the fault, classify the severity, and execute that stepwise active short circuit within the 60-millisecond window we talked about.
Because it's a high-fidelity physics model, they can monitor the simulated mechanical shear forces on the virtual rotor shaft.
Yep. They verify that the two-stage magnetic cushion keeps the torque ripple below, say, 5 Newton meters, ensuring that in the real world, the transmission wouldn't literally explode.
Wow.
It allows engineers to test thousands of edge case failure permutations that would be physically too dangerous or just too expensive to replicate on a real dynamometer.
It's just a staggering orchestration of engineering disciplines. I mean, from the quantum mechanics of parasitic inductance and copper to the algorithms orchestrating asymmetrical short circuits to mass spectrometers sniffing for helium atoms. Every time a driver steps on the brake pedal of a modern electric vehicle, this invisible silent war is being waged under the hood in fractions of a millisecond.
It really reframes the complexity of what we take for granted every day.
It really does.
And, this raises an important question based on a rather profound detail tucked away in the very last paragraph of the source document.
Oh, what's that?
It offers engineers access to advanced Python simulation models for transient coupling.
Oh, models designed to simulate the parasitic inductance and voltage spikes entirely in software before a single physical prototype is ever built.
Exactly. It highlights a massive paradigm shift in automotive engineering. We used to build physical prototypes, break them, and then reinforce the weak points.
Right.
Today, the sheer speed and violence of high-voltage electronics mean you can't rely on physical trial and error. The safety of a 70-mile-per-hour vehicle is dictated by digital twins.
Wow.
The exact geometry of a copper bus bar, the specific millisecond a software loop triggers a short circuit, the precise point a silicon junction will melt,
Yeah.
is all predicted and optimized by a line of Python code running millions of iterations in a virtual space.
We are essentially trusting virtual realities to ensure our physical survival on real-world highways.
We are.
It begs the question, as our powertrains become ever more powerful and the switching frequencies get faster, how far can digital foresight push the physical boundaries of materials before we hit a hard limit? Just something to think about. Next time you hit the brakes and feel that smooth, silent deceleration, just remember the absolute chaos that is being mathematically suppressed beneath your feet. Thank you for joining us for this deep dive. We'll catch you on the next one.